Okay. So it's a great pleasure to me to introduce the first speaker of this conference, Sobhan Seyfaddini, from, okay, thank you, from Institut de Mathématiques de Jussieu. He will talk about the algebraic structure of groups of area-preserving homeomorphisms on surfaces. Okay, thank you.
Thank you very much. Many thanks for the organizers for their invitation. It's a great pleasure for me to be here in Bedlevo, and it's my first time actually taking part in this series of conferences. So I'm very much looking forward to learning a lot of stuff. So with that said, let me just say that the works I present today are based on several different articles jointly with Dan Cristofaro-Gardiner, Humiliére, Mak and Smith. Okay, so let's get started. I'm going to begin my talk with an old theorem of Albert Fathi from the 1970s. I believe at that point in time, he was actually a student, a PhD student in Orsay, and he was interested in the group of compactly supported volume-preserving homeomorphisms of the n-dimensional disk or the n-dimensional ball. So that's what the notation stands for. Let me see if I can use the pen. So you see the C you see here, the C you see here stands for compact support, meaning we're considering only those homeomorphisms which are identity near the boundary of the ball. And here's what he proved. He showed that this group, so compactly supported volume-preserving homeomorphisms of the n-dimensional ball, is a simple group when n is at least 3. Okay, so it has no non-trivial proper normal subgroups. Okay. Maybe I'll make a quick remark in case some of you are wondering why we are imposing this compactness assumption. The reason for that is that, why are we not looking at the larger group of all volume-preserving homeomorphisms? Well, the compactly supported homeomorphisms form a proper normal subgroup. So from the point of view of the simplicity question, it's only interesting to pose the question, compactly supported homeomorphisms. Okay. That's the reason for that assumption. Now, as you could see, Fathi's theorem leaves out the case n equals 2, the two-dimensional case. The one-dimensional case, in that case, the group is trivial, so there's nothing to ask. So the only thing that's left open is the case n equals 2. And this is the question that he asked in his original paper. Is the group of compactly supported area-preserving homeomorphisms of the two-dimensional disk a simple group or not? Any questions about the theorem or the questions? Simple questions, and the statement of the theorem is simple too. One thing I'll point out is that as a topological group, this is indeed simple. This was already known in the 70s when Fathi was working on this. So the group does not have any closed proper normal subgroups. This is part of the reason that this question was challenging. It's kind of hard to identify proper normal subgroups, at least at first attempt. Yes? Yeah. So you mean for diffeos, it's simple, and we'll get to that. There is a slide on I've prepared on various groups that we'll get to. But so, for example, for diffeomorphisms of the n-dimensional ball, preserving volume or not preserving volume, it is simple, and this was proven by Thurston in the 70s. There was a whole industry of studying various transformation groups and checking whether the groups are simple or not in the 50s, 60s, and 70s. And I'll get to the history. It's a kind of a long and beautiful history. Great question. Other questions? Okay, so as you could see, given Fathi's theorem, simplicity for n greater than or equal to 3, and this remark about the grouping topological is simple, one might at first glance think that the two-dimensional cases should be the same, that the group should indeed be simple in dimension 2 as well. However, over the years, many people thought about this question from various communities, actually, and eventually, around the early 2000s, so around 20 years ago or so, within the symplectic community, a consensus was formed that somehow the symplectic nature of area in dimension 2 should force the existence of a proper normal subgroup. Okay, so in fact, a conjecture was formulated that the group is not simple, and it's called the Macduff and Solomon in their textbook on Introduction to Symplectic Topology refer to this as the simplicity conjecture. I would have called it the non-simplicity conjecture, but they're the ones who wrote the book. Okay, so the simplicity conjecture says that the group of area-preserving homeos of the disk, which are identity near the boundary, is not a simple group. And the main result of today's talk, and the goal of this lecture series to sketch the proof of this, is that the simplicity conjecture is indeed true, and the group of compactly supported area-preserving homeomorphisms of the disk is not a simple group. Okay. Any questions about the statement? I have a couple of remarks if there are no questions. So first remark. Right, so in around 2009, Frédéric Leroux showed that assuming the group is not simple, then it has gazillions of proper normal subgroups. There are infinitely many, and he obtains many it has a very beautiful construction of various normal subgroups, proper normal subgroups. Now, I can give you an example of a proper normal subgroup. Here's one. The commutator subgroup turns out to be a proper subgroup. So this is the subgroup generated by the commutators inside. Now, our proof actually doesn't show this directly. We prove the group is not simple. We'll see how. And then it follows from a priori knowledge that was there from many years ago that the commutator subgroup has to be a proper normal subgroup. In fact, it's the smallest. So you have just want to give you an example of a proper. And the second remark is that the proof requires ideas from symplectic topology, symplectic geometry. And this might come to you as a bit of a surprise, at least at first glance, because symplectic topology, it's a subfield of smooth differential topology, symplectic manifolds, symplectic forms, symplectomorphisms. These are all smooth objects. So what do they have to do with homeomorphism? That's a very legitimate question. And now, if people have no questions on what I've said so far, I'll take a detour into symplectic topology to tell you how homeomorphism actually is. So this next part of the talk is kind of a detour that doesn't have to do with the rest of the lectures, but we'll see how homeomorphism arises actually in kind of a very natural way in symplectic topology. So let's first recall what a symplectic manifold is. So a symplectic manifold is an even dimensional manifold. So the 2n here is denoting the dimension. And it's equipped with what we call a symplectic form, omega. So being symplectic means omega is closed, the omega is 0, and then it has to be non-degenerate, which means there's a bilinear form on every tangent space. It's a non-degenerate form. Equivalently, you raise it to the power n, it gives you a top form that has to be a volume. Use canonical choice of volume on every symplectic map. Here are examples. This is the example that's most relevant to us in these talks. Take a surface and curve it with an area, like this, with a standard area. That's a symplectic manifold. You could take products of surfaces, and then you get a very rich class of symplectic manifolds. And here's a historically important one. You take the cotangent bundle of any manifold. It has a canonical symplectic structure. That's these are the phase spaces in classical mechanics, and that's where the field of symplectic geometry actually originates from. Now, automorphisms of symplectic manifold are called symplectomorphisms. So these are those diffeomorphisms of the manifold which preserve the symplectic structure. This is what this highlights. This is what this equation here says. It says that your phi is preserving the symplectic. Okay, as you could see, this is equation phi star omega equals omega. This is something about the derivatives of the map. It says the derivative has a certain property. It's a symplectic matrix. That's what it's. Keep in mind, it's a C1 condition. It depends on the derivatives. And examples of symplectomorphisms are again area preserving. Now, before I could tell you how homeomorphisms arise, I want to recall for you kind of the origins of symplectic topology as a field. So, as I said in the previous slide, every symplectic manifold can be equipped with a canonical choice of a volume, and symplectomorphisms preserving the symplectic form, so are therefore volume preserving diffeomorphisms. Now let's consider the C0 closure of symplectomorphisms taken inside the group of volume preserving diffeomorphisms. So that's what this object here is. Okay, so SymPar is the set of this is closure of the symplectomorphism inside volume preserving diffeomorphism. So this is those diffeomorphisms of the manifold which can be approximated in C0 topology, compact open topology, uniform topology, whatever you want to call it, by symplectomorphism. So a priori, you obtain some object, the SymPar, that sits in between the two. It contains at least symplectomorphisms, and then it's contained inside volume preserving diffeomorphism. The question is, where does it sit between the two? Okay, this is a question that Gromov studied in the 1970s, and he found, initially found a remarkable answer. He formulated his really famous, in symplectic topology, at least soft-hard alternative. And the alternative says one of the following two statements is true. He did not know which. So first alternative is that the closure is actually just a set of symplectomorphisms, meaning you obtain nothing new in this SymPar. Okay, so you try to enlarge the group, but you got nothing new. And this is what he called the hard or the rigid alternative. And if this is not true, then he showed it must be the case that SymPar is actually all of volume preserving diffeomorphisms. Okay, so what he says is that one of these two inequalities, one of these two subsets is inequality, either this one or, writing here the part, maybe I should stop that. Okay, so one of these two is an inequality, but we don't know which one. Hold on. Okay, so this was the state of affairs in the 1970s and around, yes, there's a question. The answer, that's a great question. So, this is the state of affairs in the 70s. I'll tell you what happens in the next line. When he proved this, I don't know whether he showed this depended on the manifold or not. It could have been that this is the case for one manifold, but not all manifolds and so on. But we know the answer, actually. This, as I said, 10 years or so later, Eliashberg resolved the alternative in favor of rigidity. And he showed that on any manifold M, Symp is equal to SymPar. That's a great question, but we know the answer to now. So that's why I don't know what this exactly state of affairs was in the 70s. So this is called the C0 rigidity theorem. As you could see, it says that the condition of being a symplectic map, which was, as I said in the first slide, is a C1 condition, actually persists under taking C0 limits. This is actually a fundamental theorem in symplectic topology. It's historically speaking, it's the first major theorem of the field. Before this, there was no really big theorem that defined the symplectic topology as a field in its own right. And Arnold even refers to this as the existence theorem of the field in one of his papers. Now, not only did it give birth to symplectic topology, it also gave birth to my area of research, which is called C0 or continuous symplectic topology, which studies continuous analogs of smooth symplectic objects. And the examples of such objects are symplectic homeomorphisms. So now here, this object, so what are symplectic homeomorphisms? Just take the closure of Symp, but now inside homeomorph. So now I'm looking at all homeomorphisms which arise as C0 limits of symplectomorphisms. Okay? And this we call symplectic homeomorphisms. And the definition is makes sense. It is a well-defined notion because of the C0 rigidity theorem. Because if you have a homeomorphism which is symplectic, happens to be smooth, thanks to this theorem, you know that it's actually an honest symplectomorphism. Examples: area preserving diffeomorphisms, or area preserving homeomorphisms of surfaces. This statement just said, this is just a consequence of knowing that symplectic area preserving diffeomorphisms are dense among area preserving homeomorphisms. This is the reason, this is the connection between Fathi's question and symplectic topology. This is why we can bring the tools of symplectic topology to bear on these sorts of questions. Okay. So I'm done with my detour into symplectic topology. And we could go back to Fathi's question. if there are no questions. Yep. Right. That's exactly what I said. I mean, but yes. So there's a lemma written somewhere saying this is true, which means that they are symplectic homeomorphisms in the sense that I just described. Yes? Yes, that's true. So I'm actually just throughout assuming compact support everywhere. That is true. But I don't know if I can. It's true. Let me say. The method is the method of proof is such that you first approximate by a diffeomorphism, which is not area preserving, and then you correct the diffeomorphism, so compact support. But if you know it for diffeomorphisms, then in the non-conservative setting, then you have it for conservatives. So if you learn nothing from my lectures, but you learn the statement of the symplectic rigidity theorem, the Gromov-Ilya-Ashberg theorem, then that's great. And this is the kind of perhaps the nicest thing that the most interesting mathematical result in all of these lectures is this part that I just stated, which has nothing to do with the rest of my lectures. Okay, so if no further questions, then I'll go back to Fathi's question. So actually, I stated this question for the disk, whether area preserving homeomorphisms a disk is a simple group. But in his paper, actually, he stated a question that applies to all surfaces. And what I'll do now in this next part of the introduction is state the more general question and then tell you what happens in the more general sense. Okay. Any questions? Okay, so I have to recall for you what Hamiltonian diffeomorphisms are. Presumably a lot of people are familiar with this, but you'll recall the definition because it's important in the lectures. So suppose you have a surface and I don't suppose that the boundary is empty. It could be empty or it could have non-empty boundary like this. Now Hamiltonian diffeomorphisms of a surface or general symplectic manifold arise as solutions to Hamilton's famous ODE. And this is how, let me quickly recall the notation and the definition. So you begin by taking a time-dependent Hamiltonian H. So the 0, 1 here stands for the time variable and the Hamiltonian is just a time-dependent function on the surface. And if the surface has boundary, I assume that the Hamiltonian just identity is 0 near the boundary of the surface. Now, using the symplectic structure, you could associate to this a vector, which in a coordinate-independent way is defined by saying it's the vector field, which once you plug into the first component of the symplectic form, gives you back the differential of the Hamiltonian. In local coordinates, so if you just take standard XY coordinates on the disk, the case that most interests us is given by XH is dH dy minus dH dx, Hamilton's order. H depends on time here, and so this vector field is actually time-dependent vector field. I've dropped the t variable from the notation. Now, you could integrate this vector field, and it gives you an isotopy of the manifold of the surface. And these are called Hamiltonian isotopies. And the set of all diffeomorphisms which can be reached in this way are called Hamiltonian diffeomorphisms. Now, so the notation for the set of Hamiltonian diffeomorphisms is usually in symplectic. This notation is ham of sigma. And it's an easy lemma to check that these are all area-preserving diffeomorphisms of the surface. So they're symplectic diffeomorphisms on the surface. The 0 I've put here, it stands for identity component. This stands for the identity component, which is obvious because they're time one's maps of vector. Okay, so let's examine 3 surfaces. In the case of the disk, ham just turns out to be just all of area preserving diffeomorphisms, which are identity bound. Area preserving this. In the case of the sphere, you get all area and orientation preserving the fields of the sphere. But for other surfaces, you get a proper subset. Actually, it's a proper normal subgroup of the identity component in area preserving. Now, the 2 cases that perhaps are most interesting to us are the disk and the sphere. Now, here's a definition for Hamiltonian homeomorphisms, which is very much analogous to that of symplectic homeomorphism. Let phi be an area-preserving homeomorphism if the surface has boundary, I suppose that phi is identity near the boundary. I say it's Hamiltonian if I can write it as a limit of Hamiltonian between them. So it's just identical to the definition of a symplectic limit. And then I denote the set of Hamiltonian homeomorphisms of the surface by Ham bar. Note that these are all identity near the boundary. This is kind of important technical. Let's examine our surfaces from the previous slide. The disk, you get area preserving homeomorphisms of the disk action. So in fact, the symplectic homeomorphisms of the disk are the same as its Hamiltonian. In the case of the sphere, you get area and orientation preserving homeomorphisms. And for other surfaces, you get a proper normal subgroup inside all area, inside the identity component of area preserving homeomorphisms. Fathi's question in full generality was, is this group, Ham bar, is this a simple group? This is the question he asked. I showed you that it is not simple for the disk, and I'll tell you what the answer is for the other surfaces. So before I tell you the answer to this question, I want to review a little bit of Fathi's work from the 70s, so to give you the context on how he arrived at this question. Any questions about the question? Okay, so Fathi's work from the 70s. Consider, let M be a compact manifold with or without boundary equipped with a volume. Now, he was interested in the component of identity in the group of volume preserving homeomorphisms of the manifold, and he wanted to know if this is a simple group or not. Okay. So the special case of the surfaces is what we specialized to later. Okay. This is what he was interested in studying, and he succeeded in largely answering this question. And here is a 3-line summary of his beautiful paper from his PhD thesis. He showed he constructed a homomorphism, which he called mass flow. This is what I'm denoting by curly F. Out of our group and into a certain quotient of H1 of the manifold. So the first homology of manifold with real coefficients. This gamma here is not important. You could pretend it's zero. It's just, you should know it's a discrete subgroup. So it, the image is non-zero as soon as H1 is non-zero. So look, he constructed a homomorphism out of the group. If this homomorphism is non-trivial, then the group is not simple because you just take the kernel. And I should say that construction is extremely natural. I mean, it's basically the mean rotation. So the kernel of this homomorphism gives us an obstruction to the simplicity of the group. And as soon as it can be non-trivial, it is non-trivial. So if H1 is non-trivial, this kernel turns out to be non-trivial. Okay? So then it tells you that the manifold is, the group of volume preserving homomorphism is not simple if H1 is non-trivial. And what happens if H1 is if H1 is actually trivial, then you have to know what happens to the kernel. He showed that the kernel itself, which is the obstruction to non-simplicity, is actually a simple group in dimensions greater than or equal to 2. So you see, the picture is quite simple. Either the group is simple, or if it's not simple, it's because of existence of this natural homomorphism whose kernel itself, the obstruction to simplicity, is itself simple. So they're not too far from being simple. And as you could see, there is again the case n equals 2, which is left open. Oh yeah, so there's the corollary that I wanted to point out. So if you take the manifolds Sn, the sphere of dimension n, or the disk of dimension, these are simply connected manifolds. So the kernel is everything. And Fathi's theorem tells you that for these groups, the group of volume, for this manifold, the group of volume preserving homeomorphisms is a simple group. Now, what's left open is what happens in dimension 2. And this brings us back to Hamiltonian homeomorphisms of surfaces. It just happens, take this as a fact, that in the case of surfaces, the kernel of Fathi's homomorphism is exactly that group of Hamiltonian homeomorphisms of a surface. That's why he posed the question. Yes? In the proof. Okay, so that's a great question, actually. So he has a fragmentation I'll state for you what the fragmentation lemma is for the ball. So here's the ball of Dn, greater than or equal to 3. He says take F, a volume preserving homeo of the ball. Then you could write F as the composition of two homeomorphisms, F1 composed with F2, with the following property. Support of F1, support of Fi, is contained in a topological ball Bi, such that volume of Bi is equal to 3/4. The 3/4 itself is not too important. It's the fact that this is less than 1. Volume of the ball. So this sort of fragmentation theorem, you could take something that's supported everywhere and write it as the composition of two guys that are supported in smaller balls. If this were true in dimension 2, he proved this in dimensions 3 and higher. If this were true in dimension 2, then you'd have simplicity. And before this, we did not know. Now we know this is not true in dimension 2. Now, why? So this doesn't exactly, so this is what failed in dimension 2. And why does it fail? Well, if you go through the proof, then you see that in the course of the proof, he does pick something like this. C is an arc. So it's it's like a embedding of an interval into the ball. He takes an embedding of the interval to the ball, and he looks at F of C. And you get something that, well, it's identity, so it looks like you get something that, well, it looked like that. What he needs is that the complement of this is connected. Clearly, this is not true in dimension, but true in dimension 3 and 5. So this simple statement that's only true in dimension 3 and higher is the obstruction to his proof, and it turns out that it's things fail in dimension 2 for good reasons. That's a great question. Yes. Yes. So I'm taking F in B is the ball or the disk, actually. Maybe I'll call it D. It's just I'm taking here compactly supported homeomorphisms of volume preserving homeomorphism. So the fact that this simple statement is not true in higher dimensions is responsible for what we see in dimension 2. Okay, so the theorem, the most general theorem that I state today is that in fact the same thing that happens in the case of the disk is also true for all surfaces. Hamiltonian homeomorphisms is never as simple. Okay, and this we proved a little later than the initial theorem, and this is joined with Cristofaro-Gardiner, Humiliére, Mak and Smith. Actually, when I give the proof, we'll just go back focusing on the case of this, but I wanted to give you the more general state. Some remarks. In the case sigma equals S2, this tells you that volume preserving homeomorphisms of the sphere is not simple. And this we had already proven, actually. The case of the disk, which I mentioned, and the case of the sphere, we had already proven in separate papers with Cristofaro-Gardiner and Humiliére, and used there a flavor of Floer homology called periodic Floer homology, which we will not see in this lecture. However, what we use in the course of this more general theorem is another flavor of Floer homology called Lagrangian Floer homology, and I'll try to make an introduction to that. I see that my line was cut off, so let me go back. So this was inspired by works of Oshvath and Jabo and Higard Floer homology, Mak and Smith, an earlier work of Mak and Smith, and Woltrovich and Schlup. Sorry, there's 3 lines that were erased there accidentally. Now, at this point, these things probably might not make much sense, but the reason I mentioned this was periodic Floer homology and the other one's Lagrangian Floer homology is because the 2 flavors of Floer homology used here are very different, and Lagrangian Floer homology is considered a much simpler form of Floer homology. Periodic Floer homology, its existence depends on what's called Seiberg-Witten theory. It's, one is Lagrangian Floer homology, you need 500 pages. For periodic Floer homology, you need 500 to put the theory on sound. So this is a significant simplification from that viewpoint. Okay. If there are no questions about the main statements, then I will recall for you a little bit of the history which we talked about, and then I'll move on to the. So it turns out that this simplicity question has a very long and interesting history that goes back to at least 1935. And This, in 1935, Ulam posed the question of whether the identity component in homeomorphisms of the N sphere is a simple group. And as you could see, this I took from a slide by Etienne Gis. This is a scan of the question. So it was problem 29 on the Scottish book. I can't read Polish, but I assume somebody can read and confirm that this is actually true, what the translation to English is actually true. Or maybe the handwriting is not so great. Okay, so and again, the reason they put the identity component here is the same as that compactness assumption. The question is only interesting for the identity. So it's a long and nice history. It's a very old question, and kind of coincidentally very nice that the question was first raised here in Poland. Now it was answered for n equals 1 by Schreier and Ulam in 1934. So a year before the question was actually posed. And presumably that's why Ulam actually posed the question a year later. And for n equals 2, Ulam and von Neumann, so for the two sphere, actually resolved this in 1947. I saw the paper myself. There's no proof in it. It's 4 lines, and they just say it's true. They say something about it, but maybe people wrote shorter papers. Now, real progress towards this question actually came several decades later. And this was in the 1960s, when a combination of results by Anderson, Fisher, Chernavsky, Edwards, and Kirby led to the proof of simplicity for homeomorphisms of any manner. So it's always. Then the case of diffeomorphisms, which you asked about, people studied this case in the 1970s. It came up in Thurston's work on classification of foliations. And again, it turns out the group is simple, and it involves a beautiful body of work by Epstein, Hermann, Mather, and Thurston. Now, so far we saw the groups are simple. But if you go to the conservative setting where there is a volume form, yes? Nothing. I mean, I'm always looking at identity component compactly supported if the manifold is not closed. There is one case. Here I'm assuming there's the question of regularity that was raised. Okay, here I'm assuming that this is C infinity maps in the case of diffeomorphism. When you lower regularity, the question becomes very subtle. Mather's proofs actually settle it for CK, for all K, CK, except for K not equal to dimension plus 1 or something like this. Thinks this proof doesn't work. That's still open. So C2 diffeomorphisms of the circle, we don't know if that's simple or not. So there are still some open questions left around here. Okay, so as I said, now back to the conservative setting, this is when the groups are not necessarily simple. And the reason for non-simplicity in each one of these cases, volume-preserving homeomorphisms, volume-preserving diffeomorphisms, or symplectomorphisms, is the same general philosophy. In each of these cases, there exists a natural homomorphism out of the group. Symplectic geometers call them flux. Fathi calls it mass flow. People in dynamics, mostly, they prefer to refer to it as mean rotation vector, perhaps. And that's the obstruction to simplicity, it's kernel. But the kernel itself, so the obstruction is itself simple. We're never too far from being simple. And the last on my list, at least, is the group of Hamiltonian homeomorphism surfaces. This is not simple, but the reasons here are different. They have to do with symplectic geometry. We're not able to construct the natural homomorphism out of this. We do construct a homomorphism, which I won't talk about actually here, out of the group, but it uses axiom of choice, and it's no way canonical or natural. And there are lots of normal subgroups. I mean, the situation is really different. And that's the end of the history of the question, kind of the end of the introduction to the talk. So if people have no questions about what I've said so far, then I'll move on to begin to talk about the proof. Yes, at least. Okay, so it's related to the C0 flux conjecture, but we could put that aside. So you are right. There is an open question. What happens to this Ham bar? You could make sense of it in any dimension. There's the C0 closure of Hamiltonian, if you want. That's an open question. I'd say that's the $1 million question, because for a long list of reasons, the proof is very two-dimensional for a long list of reasons. But one is that the Floer homology we use is only defined in dimension 2. It has something to do with the fact that Seyfaddini equations only exist in dimensions 3 and 4. So to settle this question in higher dimensions, one would have to find a replacement for the machinery of Seyfaddini Floer in higher dimensions. That would be the first obstruction. And then even if that's done, there's lots of things that use two-dimensional. Yes. No, we know nothing. That's yeah. So we know nothing. The only thing we know is that the commutator subgroup, so the smallest one there is one, the commutator subgroup. So if you take the commutator subgroup of Ham-bar, this is a simple normal subgroup. Everything else, any other normal subgroup, contains this one, and they're in between, all of them. So we know that this is the smallest one. In between, there's a lot, and we don't know much about any of them. So one interesting question would be to look at the quotient. The most natural quotient to look at is Ham-bar by this commutator subgroup. That's all I can say. Nothing else. I get asked this question all the time. I've thought about it. My collaborators, we've all thought about it. Can't say anything about it. Yeah. Great question. Other questions? Okay. So we start the proof, or start looking at the proof. And now, so I'm going to outline non-simplicity of Hamiltonian homeomorphisms in the case where the surface has non-empty boundary. And the reason I do this is actually because in here there's a very beautiful story to tell in connection with what's called the Calabi invariant. And actually, for the proof, I'm just going to assume sigma equals T, so it's the disk. So again, maybe I think I'm going to drop the notation Ham-bar for the rest of the talk. We're going to so Ham-bar is just going to be area preserving homeos of the disk, and Ham, recall, is area preserving diffuse of it. So we're back in the case of this where a lot of the stuff I told you up to now is just forget about. Go back to the case. I learned recently, just around 2 weeks ago, that Calabi will turn 100 on May 11th. So, happy birthday. Okay, so what's the Calabi invariant? It's actually a homomorphism out of the group of area preserving diffeomorphisms of the disk and into the real line. Okay, so the area preserving diffeomorphism disk, then we know is not simple because it admits a non-trivial homomorphism. And here is its definition. Take an area preserving diffeomorphism of the disk, say phi. Since it's Hamiltonian, I can write it as the time one map of some Hamiltonian, which I call H. So when I write phi equals phi sub H, I mean it's the time one map of this Hamiltonian isotopy given by some H. And we take H to be 0, recall, from near the bound. Now here's the definition. It's about as simple a definition as you could see. The Calabi invariant of phi is just the average of this Hamiltonian over the surface. So you take average with respect to the space and time. It's about as very simple definition. What's not obvious is that first, it's not obvious that this is well defined, because if I take phi, I could have two different Hamiltonians that give you the same path. Now it's a minor miracle. There's a computation. It turns out that it doesn't depend on the choice of H, so it's well defined. And there's kind of a simple computation that tells you it's a homomorph. Now, so we have this, so we have this homomorphism that's defined on the group of area preserving diffeomorphisms of the disk. All right, there is a connection that I should point out here. Maybe it comes up later in lectures. If you notice, just the simple estimate tells you that the Calabi, actually, I should have put an absolute value sign around absolute value of Calabi is less than or equal to the sup normal. That's just obvious. Okay, so now we have the group of area preserving diffeomorph. It sits densely inside area preserving homeomorph. Now I have a invariant, I have this homomorphism that's defined on area preserving diffeomorphism, so on a dense subset. The question is, can you extend this to the entire group of area preserving homeomorph? So this is a question that was, right, can be extended. This was already posed in Fathi's question, and then Gis has this beautiful talk from ICM 2006 with lots of beautiful, famously beautiful talk with lots of beautiful pictures, and he poses that question there in that talk as well. The reason for posing the question is the same, as you could guess. Well, if we can extend the Calabi invariant to area preserving homeomorphisms, then we have an answer to our question. We know that the group will not be simple. Take the curve. Okay, so let's see. Can we take, so what the question is asking is whether, we could take limits and just extend by taking limits, the Calabi invariant from a dense subset to the whole. There's a problem with this thing. And the problem is that the Calabi invariant is just not continuous in the C0 topology. And so just the naive approach just has no chance of working. And I'll give you an example showing you why the Calabi invariant is not continuous in the C0 topology. So what you should do here, take a sequence of Hamiltonians Hn, functions Hn, depend or not depend on time. You take them such that they have very small support. So they are supported in a disk of diameter 2/. And you could pick them to be pointy enough such that the average over the disk is actually 1. But then the Calabi invariant just by definition is 1. And these things are converging to the identity in C0 topology because the support is got the distance from identity is at most 2/n. And so it's clear that the Calabi invariant is not continuous in C0 topology, and you just cannot extend it in some sort of, the naive approach just has no chance of working. So it might turn out to be not such a great question, but actually, this is what we try to do. And this was, in fact, suggested by the works of O and Muller from the 2000s. So what O and Muller did is, in hopes of solving this Fathi's question, they introduced an intermediary normal subgroup, which they call hameo of the disk. Note that this is hameo. This is an A. Right? Well, this is an A, as you could see. It's not homeo. This is the name they picked, hameo of the disk. I'll give you the definition in a second. It turns out to be a normal subgroup of area preserving homeomorphisms. The hope was to show that it's a proper normal subgroup, but that's not easy to show, but it has a connection with Calabi invariant too, as you'll see. So here's the definition of this group. I take an area preserving homeomorphism of this Phi. Then I say it's in this subset, is in this hameo, if I can do the following. Find a sequence of smooth Hamiltonians Hi with such that the associated diffeomorphisms converge in C0 topology to Phi. Oh, it started writing. Great. So it converges in C0 topology to Phi. And the second condition is that, and this is the second condition is the important condition, that the HIs converge, the HIs, the Hamiltonians themselves, they converge to, in sup norm, to some limit H. The first condition is actually just vacuous because it's always true. Without the second condition, that gives you nothing new. It just gives you the entire group because every homeomorphism can be approximated by diffeomorphism. Now, the hope is that by imposing this second condition, you get something more interesting, the convergence of the Hamiltonians in the sup. Okay, so now just to imitate the notation in the smooth setting, we write Phi equals Phi H. Okay. Now, they checked in their paper that this hameo is actually a normal subgroup. They hope to show it was, the conjecture in the paper that's actually a proper normal subgroup, but that's not, that turned out to be difficult to show. Now, so they introduced this thing, and then it turns out that in conversations with Fathi, O and Fathi together, they suggested another approach to solving the conjecture. And they suggested maybe we could try and extend the Calabi invariant to this intermediary sum. I'll tell you why they did this. But the reason they suggested this is because there's an obvious definition that's just sitting around it. You take a homeomorphism phi that's in Hamil. It has some associated Hamiltonian H. So just repeat the definition from the smooth setting for Calabi. Right, so I define Calabi of phi to be the average of this continuous Hamiltonian. In 30 seconds, I'll explain why they wanted to do this. Okay? Now, so you have some numbers, but of course there are things to do. And first, you must show that this is well defined. Remember, in the smooth setting, I refer to this as like, this is what's different. So what do we have to do? You have to take a phi. It might have two different Hamiltonians associated to it. So let's call them H and G. And then you have to show the average of H is equal to the average of G. And Hamiltonians are associated to phi is via this limiting process that goes into the definition. Okay. This turns out to be the difficult part of the story. Now, it's, in the smooth setting, this was call it a minor miracle. It turns out to be kind of this rather simple but clever computation. But to show this in the C0 setting, this turns out to be quite hard. Once you have this, then O already showed in his paper that this defines a homomorphism. So the definition, the proof that Cal defined a homomorphism, the smooth setting actually goes through once you know it's well defined. Okay, we are going to show that it's actually well. That's what we're doing. Now, why did Fathi and O suggest we do this? It's for this reason. Suppose you actually extend Calabi to Hamil via the definition I put on the previous page. So let's just assume it's well defined. Then you have an answer to the Fathi's question. The group is not simple for the following kind of simple reasoning. If Hamil is proper, that was originally the hope. Hamil turns out to be proper. Good, you're done. You have a proper normal sum. If it's not proper, then it's the whole thing. You've extended Calabi, therefore you've extended Calabi to the whole thing, and you have a kernel. So then you're done again. So this was the logic behind this approach that was suggested by Fathi. And so the theorem that we'll show in these lectures is that actually this is the case. Calabi extends in this way to this group Hamil. So now we know the answer. Yes. Both. So it turns out that we actually show that Hamil is a proper normal subgroup. Okay? And the reason actually it's very plausible because once you take so Hamil turns out to be a proper normal subgroup, and Calabi extends to Hamil in this way. And this is not too surprising. You could reconcile this in this way. I can find a homeomorphism of the disk that imagine that is spinning the disk. So it just depends on the radius, and it's spinning the disk faster and faster, and it's just so fast that it blows up at the origin. It's given by a Hamiltonian that looks like this. I mean, if this is 0 in radial coordinates and this is 1, a Hamiltonian that just blows up extremely fast, such that the average of H equals infinity. This gives you a homomorphism with one point of singularity, smooth everywhere, but its Calabi invariant is infinite. And you could show that this is, if Calabi invariant extended to the whole disk, this would have to have infinite Calabi. So then you could use this reasoning to show that it's actually not. Great question. Other questions? Okay, so how do we extend Calabi? I haven't said much about symplectic geometry. Oh yeah, so actually we extend Calabi for any surface. As I said, I'm focusing on the case of the disk, but for any surface with boundary, the Calabi invariant is well defined, and we do the same argument actually works in all surfaces. So this is the statement we are going to prove, and what I'll do now is give you the outline of the argument. I think it will be helpful for the next part of the talk to remember the definition of, not right away, but you'll remember the definition of Hamilton. I'll write that on the board. So we say phi is in Hamilton if there exists HI smooth such that phi HI C0 converges to phi and HI have a limit in sup norm, which I call H. For that fast spinning Hamiltonian, the limit would have to be the same as infinity of the origin. So, okay, and now here's where the tools of symplectic geometry come. So we use Lagrangian Floer homology, and a part of the goals for my lectures is to give a mini course on what this and the related form of Floer homology are, to define a sequence of invariants for area preserving maps of the disk. So these are called C sub D. D just ranges over the natural numbers. Each CD takes in area preserving diffeomorphism and gives you back a real number. We'll see that. Now, obviously, the story has to somehow tie in with the Calabi. We prove that these invariants recover in the limit the Calabi invariant of phi. Okay, so I fix a diffeomorphism phi, and then it turns out that this limit of CD of phi as d goes to infinity is the Calabi invariant of phi. And this is part of the miracle of the story, is the construction of these invariants is quite involved. It involves the use of Lagrangian Floer homology, as I said, and on the surface, they have nothing to do with the Calabi. But then in the limit, they recover this classical invariant, which is the average of the Hamiltonian of the limits. Now, the story has to obviously tie in some way with homeomorphisms, and that comes through the next statement. We prove that the CDs, although they're defined for diffeomorphisms, they can be extended to homeomorphisms. Okay? So for each fixed D, CD is C0 continuous and extends continuously to homeomorphism of the disk, area preserving homeomorphisms. So these invariants, which are defined via Floer homology, which is an extremely smooth tool, somehow extend to homeomorphisms, and this way we are able to define Floer theoretic invariants for homeomorphisms. And now, once you have these three components, yes. The O-Schwarz spectral invariant. Sorry. Okay. I thought you said O-Schwarz. Yes and no. There are similarities between the two, but this is more involved. This is more involved. But there are similarities. There's fragmentation lemmas and so on. This is where you use tools from dimension 2. This is 0. So what's two-dimensional here, since the question came? Item 1 is two-dimensional. This form of Lagrangian Floer homology is not a two-dimensional tool, but the form we use here is purely two-dimensional. Item 2 is two-dimensional. Item 3 is two-dimensional. Dimension 2 is used everywhere. Okay, so now let's suppose we have these three invariants CD with these three properties, and using these three properties, I'll try to convince you that the Calabi invariant extends to this group of homeomorphisms. So remember what we have to show. We have a homeomorphism phi with two different Hamiltonians. So let me just spell this out. I have to spell it. So that means I have this sequence HIs that converge, but I also have a second sequence GI such that this happens. And GIs converge in sup norm to G. And what we want is that the average of G is equal to the average of G. That's what we need to show. Now, what we'll do is, it's a simple argument. It's not too hard. You could suppose, reduce quickly to the case where, say, G is 0. So phi is identity, and G is 0. So suppose G is 0. for the case, so you reduce to the case where actually the convergence is taking place towards the identity. And now we have what we want to show is average of H is 0. It's easy to reduce to this simpler, a priori simpler case. But what you have to keep in mind is that this H is a C0 function. It's not a smooth function. And so here's the definition of Hamiltonian, which I've recalled on the slide, which is on the board as well. And now we'll try to prove it. Okay. So I'm going to put a sequence of inequalities on the slides. On the left-hand side, you have average of H, the absolute value. We want to show it's 0. So there's going to be a sequence of inequalities, and the right-hand side eventually 0 will appear. Yes, I tried to simplify. Yes, the big integral sign is this thing. I mean, this is a time-dependent thing. So big integral of H is notation for this. So I fix a t first and integrate with respect to omega over the disk. And then t ranges in S1 or 0, 1, but then I do a dt. That's what the big integral sign is. Thanks. Okay. So let's see what I do. So first I do, most of the steps are actually quite simple. It's just you reduce to the case where you could apply the three properties from the properties from the previous slide. So I added, subtracted average of HI and added it back in. So this is just a triangle inequality. And then the second term is the second term here. So the second term here, I'm just adding and subtracting CD of phi HI. Doing this so that I could use the properties from the previous. Now I do something that might, at least at first glance, look not so useful, but turns out to be useful. What I did from going in this line to the next line, I took this term and again applied the triangle inequality. Oh, no one did this. I applied the triangle inequality here by adding CD of phi j. So I added an extra index j, and I added it back in. It might look like a silly thing to do. It just makes things at first glance worse. But note that the j and I are kind of decoupled, and the j is actually. We'll see why this helps out. And now there is a fact about these invariants that I'll use at this step, which I did not state yet. In symplectic terminology, we call this Hofer continuity, and basically it says the following: the CD of phi HI minus CD of phi HA is bounded above by difference of supernormal difference of HI and H. So CD is actually Lipschitz continuous with respect to the soup. Okay, so we take this and we plug that back in. So this then here I just replace this inequality, this term of the inequality with HI minus H. Okay, so I'll go to the next slide, and this bottom line will be at the top. Okay, so now what I'll do is I start taking limits. I have three indices, I, J, and D. And I'm going to start taking limits as each one of them goes to infinity. And you have to do it in careful order, or else you won't get the answer. So, luckily it's written on the slide. So, hopefully, correct. So first, I'll take limit as j goes to infinity. Now, note as j is going to infinity, these phi j's they're converging to the identity. This is where I'm assuming that phi is identity. And I said CD is continuous. You fix it, CD is continuous in C0 topology. So CD of IJ has to converge CD of identity, and that's just known as 0, generated by the 0 Hamiltonian. Okay. So if I do this, then my inequality immediately simplifies, and I got rid of that last term, the CD of IJ. I got rid of this term, and I also simplified this J and replaced it by an H. Now we have to take limits with respect to D. Let D go to infinity. And now I use this connection of these invariants, the fact that these invariants in the limit recover the Calabi. So I is fixed here, and I'm taking limit as D goes to infinity. And this was one of the properties that was on the slide. In the limit, CD of IHI converges to the average of the Calabi. Okay, so that tells you that actually this second term in the integral here, this one vanishes. So I'm left with the last term. And now it's obvious because HI is a pick to converge. This is one of the properties of these. I mean, this is what went into the definition of these. So now, we conclude that the average of H. So this is the outline of the argument. Are there any questions about this? I mean, the summary is this. You take this, you construct this invariance with those properties, and the rest is kind of a simple argument that works in this way. Obviously, we found this argument first and then went after DC. So to recap what I did today, what remains to be done to have actually a rigorous proof of Fathi's question, we need to construct these spectral invariants, what the CDs, which are called linked spectral invariants. That's just terminology. Then we need to show they have all these nice properties. They recover the Calabi invariant, they're C0 continuous, they're Lipschitz with respect to this Hofer norm or the Soup norm, as I said. Once you do all this, you put everything together, as I just explained above, and you have the solution. That's kind of the goal of the talk. Most of the talks I'll give will be concentrated on defining these invariants in some settings, and I'll prove that they recover the Calabi, but I won't prove the rest of it. And finally, let me just point out that there are other methods for proving more or less the same results. The same results have been now proven with other methods. As I said, there is this periodic Floer homology, which is a more complicated form of Floer homology that was defined by Hutchings. This can be used to do exactly the same thing. In fact, it was also used. It's a more complicated version of Floer homology, but it has the advantage that it uses periodic orbits, which my version doesn't. And it also leads to the solution of the closing lemma, the C-infinity closing lemma that some of you might have heard of. And recently, Oliver Ettmeyer used something called elementary spectral invariance. Avoids the use of Floer homology, but still uses heavy tools from symplectic topology like pseudo-homomorphic curves, and it still in some ways relies on theorems from Gromov, but perhaps not. It leads to a simplification of it. And that's it. I'm done for today's talk. Thank you.
Is there any hope that you could define CD sort of directly without recourse to anything differentiable? The answer is presumably no, but
not that I know. This is so kind of a more intrinsic proof that just works directly for homeomorphisms. Not that I know. I mean, it uses Floer homology. There is like an elliptic PDE that you need to write down. So our approach has no chance of doing it. I know Patrice Le Calvez is thinking about it, and some of the results that come from the machinery of Floer homology he's managed to recover with his foliation, with his transverse foliation techniques. Whether he will, maybe one day he will manage to do it. He's the guy to talk about. This can be done directly on homeomorphism. Now, I can't say one more thing about it, actually. I should have mentioned this. I mean, no one has worked this out, but there is another tool in symplectic topology that people in dynamics, especially Patrice, are perhaps more familiar with. Patrice is an expert at this, is generating function. And the generating function technology, I suspect it can be used to do everything I did on the disk and the sphere. And maybe someday somebody will work it. Now, these generating functions he did use them to construct his foliation, at least one approach. So perhaps there is something. If there's one guy who could do it, this should be Patrice. So I suppose you want to give another. No, there can be a limit. So this is, I'm sure I've thought about this. I don't have the answer off the top of my head, but I think it just gives you another normal subgroup that's going to be large. Or probably, yeah, anything you try, if you try and think for 5 minutes to write down using various things, some sort of another subgroup, it's going to be normal. It's probably going to be proper. And then you could show it's different than Hamiltonian. Thank you. Thank you.